Hi, I'm Martin, and this video is about metal-metal bonding and the possibility of quadruple and even quintuple bonding. Metal-metal bonding using d orbitals can seem overwhelming, but really it is fundamentally talking about how much the orbitals of the two metal atoms overlap, and then creating energy diagrams for the molecular orbitals. Using these, we can further explain the number of bonds we have and why metal-metal bond lengths seem to be abnormally short sometimes. They can also explain why some compounds are paramagnetic by considering the number of unpaired electrons. To begin, in organic chemistry, we're used to talk about sigma and pi bonds between s, p, and hybridized orbitals. But when it comes to two d orbitals, we get another option, delta bonding, which comes from a different type of overlap due to the shapes and orientations of the d orbitals. Let's make an energy diagram for the molecular orbitals of two metals bonding. If we start out by looking at the sigma bonding, between d orbitals, we know it's the z squared orbitals pointing towards each other. This bond has the best overlap and is therefore lowest in energy. Consequently, its anti-bonding, called sigma star, is then highest in energy. Pi bonds are when we have overlap between orbitals pointing diagonally towards each other. This produces two bonding orbitals, and they are not quite as low as the sigma bond, but consequently their anti-bonding, the pi star orbitals, aren't quite as high as the sigma star. And finally, the delta bonding happens when there is a planar overlap, and the d orbitals can produce two of these. The overlap is really small, and therefore the gap between the bonding and anti-bonding is really small. So if we count the amount of bonding orbitals we can possibly have for two metals bonding using their d orbitals, we get 5. 1 sigma, 2 pi, and 2 delta. If all these are used, we get a quintuple bond. This also illustrates another important point about delta bonds, that the larger the d orbital, the stronger the bond, since you have more overlap. This would be reflected in the gap between the delta and delta star being larger. We can also investigate the spin states of the metals using energy diagrams. For example, in these two molecular orbital diagrams for a d5 and d6 metal, in the d5 all electrons are paired, while in the d6 we have two unpaired electrons. So the spin state is 1, and the compound will be paramagnetic. To investigate delta bonds, we can use porphyrins or corals. Using these complexes around the metals lead to the x squared minus y squared orbitals being sky high in energy due to them pointing directly towards the four nitrogens. Then we can ignore the delta bonding orbital created by these, so we can measure the energy gap for only one delta and delta star orbital. This requires the metals each having 4d electrons, such as rhenium-3 or osmium-4, so that they fill up until the delta bonding orbital. Then, there are more ways of investigating the HOMO-LUMO gap. One way is to measure the NMR spectra at different temperatures. What happens then is that once you reach the activation energy to break the delta bond, the two porphyrin complexes start rotating away from each other, changing the NMR signals. Another way is to do electrochemistry on the compounds. This is done in solution, however, and will not give absolute measurements of the energy of the delta bonds, but it does give us good knowledge about them. For example, measuring the reduction potential of different metals can tell us comparatively how much easier it is to put an electron into the delta star orbital compared to the pi star. We do this by doing measurements of a d4 and a d5 metal. Or we can measure the strengths between 4d and 5d reduction potentials to figure out how strongly the 4d and 5d metals engage in delta bonding. While the 4d and 5d orbitals are the same size due to lengthened contraction, you can still expect the 5d metals to engage in stronger delta bonds due to some relativity.